Global PageRank gives every user the same order. NetworkX's personalization vector restarts the walk from each user's clicked nodes and re-ranks candidates around their actual interests. You'll build a personalized PageRank reranker that uses click history to reorder retrieved documents toward entities connected to the user's clicks. I'm Professor Pi, teaching search and IR with simple Python. Personalized PageRank solves a clear problem. A retriever gives a good list, but it's one size fits all. Different users click in different directions. We want the next results to reflect where each user actually explored. That helps in recommendation, question answering, and retrieval augmented generation when you care about entity context. It's light to run and sits neatly between retrieval and the final ranker. At a high level, the idea is simple. Build a graph that links documents and entities so authority can flow across relationships. Then run a random walk that occasionally restarts from nodes the user clicked. That restart bias pulls scores toward the user's interests. The result is a reordering of the candidate list, not a replacement of retrieval. We will build a small reranker that sits after retrieval. It uses NetworkX to hold the graph and nx.pagerank for the algorithm. You will see how clicks become a personalization vector, how we score the full graph once, and how we rescore only the returned hits. This keeps latency modest and fits standard pipelines. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, build the shared document and entity graph that all users see. This snippet builds the shared authority graph that every user would see before personalization. The NetworkX object G connects document nodes like D1 and D5 to entity nodes like graph, rag, and search, so authority can move through relationships instead of raw text alone. Calling nx.pagerank gives one global rank dictionary across the whole graph, which is a handy baseline and the source of the problem. Everyone inherits the same top nodes. The printed output highlights the globally dominant node, and that's the order we're about to make user-specific. Now we need to turn a list of clicks into the restart bias that nx.pagerank accepts. This example converts click history into the input shape NetworkX expects for personalized PageRank. The key step is turning raw clicks into a probability-like dictionary over nodes in G. Counts become mass, and that mass is distributed only to the clicked nodes. D4 gets extra weight because it appears twice, while untouched nodes stay at 0. That keeps the personalization vector grounded in observed behavior rather than inventing preferences. The printed value shows how much click mass landed on D4, and that mass becomes the restart bias when we call nx.pagerank. We already have a retriever that returned a small set of candidates. Now run personalized PageRank and reorder only those hits. This code re-ranks only the retrieved candidates instead of replacing retrieval. The search system already produced candidates, and NetworkX nx.pagerank adds graph-aware authority through personal rank. Because personalization is seeded from clicks near graph and rag, D5 can outrank documents that are globally reasonable but farther from the user's explored area. The sorted call keeps the scope tight. Score the full graph once, then reorder only the candidate set returned by retrieval. The output shows the highest personalized candidate, which matters because the graph is now connecting history to new results. Graph authority is useful, but we should not ignore what the retriever already judged relevant. Blend the scores. This snippet avoids treating graph authority as the only signal. Real, search, and RAG systems usually still need lexical, vector, or hybrid relevance, represented here by search score. The NetworkX personal rank values are normalized into boost, so they sit on a comparable scale with search score. Raising the graph weight favors documents near the user's explored entities. Lowering it makes the original retriever harder to overturn. The printed output shows the blended winner, which matters because practical re-ranking should improve relevance without blindly discarding retrieval evidence. Wrap the logic into a single re-rank function that handles missing history and filters out already clicked docs. This code turns the pieces into a small baseline you can drop after retrieval. Rerank 4 accepts a user's clicks and current hits, falls back to ordinary retrieval ordering when there is no history, and otherwise builds bias for NetworkX nx.pagerank. Passing dangling bias keeps nodes without outgoing choices aligned with the same user preference distribution. The function also filters clicked documents from unseen, so the re-ranker promotes new candidates instead of echoing history. The output shows the final top recommendation, which matters because the whole flow now connects retrieval, click history, and graph authority in one usable step. In a production pipeline, you would map document IDs and entity mentions to the same graph and run the PageRank boost per query or session. The graph can be modest in size for a single domain, and the re-ranking step runs once per query, which keeps it practical for many systems. This is a graph-based re-ranker that biases a random walk toward a user's clicks, so results favor nearby entities and documents. Use it when you have a candidate list plus click signals or session context that should nudge ordering, especially in entity-rich domains. One caution: a strong graph weight can overfit to recent clicks and push diverse but still relevant results out of the list. To improve this exact example, tune the blend weight between search score and the normalized personal rank boost. Increasing the graph weight will surface documents tightly connected to clicks. Decreasing it preserves more of the retriever's original ranking. If short, practical IR helps, subscribe and watch the IR videos.